The following training instruction goes through several concepts that every service partner should be aware of before conducting any operation on the Ingecon Sound PowerMax inverters. The idea is to cover several concepts that are shown in the following table of contents. The first topic we will cover is cable continuity, and the idea is to understand how the cables within the inverter are connected. Then we will talk about working operations within the inverters that are conducted with voltage. The final point we want to cover is focused on alarms and stop reasons, and the idea is to explain the difference between them. So let's get started with cable continuity. If you pay attention to the internal cables of the inverters, you will realize that in their ends there are letters and numbers. These letters and numbers give you information about where every cable is connected, and basically what they tell you is from where to where every cable goes. This also applies to the cables we can find within the electronic block. It is important to note that the red cables inside the electronic block are for control, the blue ones are used for signals, and the gray ones are used to measure the state of the AC and DC sides. If we zoom at the ends of the cable that we are using for this example, we can see that the cable goes from FTV2.1 to QAC.3. This information is very important if we want to substitute this cable in case it is damaged. These letters and numbers are encoded in a way that they identify inverter parts. Now we're going to explain the meaning of those codes. Every code starts with a letter, and this gives you information about the element to which the cable is connected. So if a particular code starts with an X, we know that that cable end is connected to a terminal strip. The terminal strip can be in the electronic block or elsewhere in the inverter. If the code starts with a Q, we are talking about thermomagnetic breakers. K is for contactors and relays, J is for terminals that can be found in the electronic boards, F is for fuses, U for the electronic block, RV for voltage surge arresters, they can be either AC and DC surge arresters, L for inductors, C for capacitors, R for resistances, and vent for ventilation fans. Now we know the meaning of the codes we can find at the cable ends, but is there any other way to figure it out how the cables are connected within the inverter? The answer is yes. Ingecon can provide, when needed, graphs such as the one you can see in the following image. These graphs give you information about what elements the cables connect, building up branches where we can check continuity. Let's have a look to an example where we're gonna use a graph from an electronic block. We're gonna check the continuity of the cables that connect the elements on the so-called QAC branch. We start checking continuity between X3.4 and J19.6. This is done using a multimeter such as the one that you can see on the image. The multimeter beeps when there is continuity. As we previously stated, we are going to start measuring continuity between J11.6 and X3.4. After that, we will check the electronic block terminal strip to make sure that this is working properly. Now we can carry on measuring continuity in the cables that connect different elements from the inverter to that particular point in the electronic block. This time we will use a graph similar to the one we saw just now, but in this case the graph represents all the elements that we can find within the inverter. Due to the fact that we know that the module we are working with is module number 2, we will focus on that particular section of the graph. If we zoom on the part of the graph we are interested on, we can get to see that the X3.4 has several elements connected to it. The X3.4 connection point comes with a letter written before. In this case it's a U, and this represents the electronic block. We will start checking continuity between X3.4 and X7.3. Now we will check continuity between X7.3 and IQ4.14. The next continuity to be checked is the one for the cable that goes from IQ4.13 to X7.3. We can see that if we open the thermal magnetic breaker, the beeps disappear. This is because the continuity has been interrupted. The last cable to be checked is the one that goes from the X7.3 terminal to the IQ2.14. If we do the same operation as before, that means if we open the thermal magnetic breaker to simulate that this is damaged, the beep disappears. This verification of cable continuity has finished, and we can conclude that the inverter is working properly. Let's carry on with the rest of the topics we have scheduled for this training instruction. Now we're going to talk about working operations with voltage. Sometimes it is necessary to keep voltage in the inverter to do some testing. There are three different voltage sources that we can find in the inverter: the AC side, the DC side, and the auxiliaries. Whenever you have to conduct an operation with voltage, you have to wear electrically safe footwear and workwear, dielectric gloves, and a protection mask. In the following example, we are showing how to measure voltages using a multimeter. The point of this exercise is to show how to measure voltages in some of the elements that are connected to the auxiliaries. In this example, we get no AC or DC input because they have been disconnected. The first point we are going to check AC voltage is at the auxiliaries input, and as you can see in the image, the voltage we get is around 220 volts. The next measuring point is the Q aux, that means the auxiliaries thermal magnetic breaker. Then the XD terminal, where we get the same reading. The last point where we're gonna measure AC voltage is at the 15 volts power supply input. The next measurements are for DC voltage, and the first point we are gonna measure is the output from the power supply. From the 15 volt power supply output, the power goes back to the XD terminal. The measurement we get is also around 15 volts. To finish with this training instruction, we're gonna give a brief explanation of what is an alarm and a stop reason and the difference between them. Both alarms and stop reasons can be accessed from the display and from the engine console manager. In this example, however, we're gonna access these alarms and stop reasons only from the display. The alarms are indicated in the main screen and they are accessed by pressing the escape button. In the case of stop reasons, we have to access the main menu, and there you can see a label where it says stop reasons. When you press OK, you access the next screen where you can get to see a list of stop reasons that have happened in the past. The stop reasons have been arranged by the inverter following the hour and the date when they occurred. If needed, this list of stop reasons can be deleted by pressing reset. Now is the moment to explain the difference between a stop reason and alarm. Alarms do not always stop the inverter. A good example of that is, for example, the temperature alarm or the insulation failure alarm. In the case of a temperature alarm, we can say that, for example, there are instances where the inverter gets hot, but it doesn't stop. Basically, what the inverter does is to regulate the power that is injecting on the grid, and instead of working at the nominal power, it works at a lower level. In the case of stop reasons, we can say that stop reasons do always stop the inverter. The list of stop reasons is larger than the list of alarms, and we can say that every alarm can have more than one stop reason associated, but every stop reason can only be associated to a single alarm. This is illustrated in the graph that you can see in the image.